Hi, so we're going to talk about how to implement shell sort. So we've already said that and saw that shell sort uses insertion sort, and the only difference is now we have gaps that can change. So let's convert insertion sort to use an additional gap parameter. And where are we going to use gap? And that's basically everywhere where we use the number 1 because that used to mean, the gap is just one position apart. So I identify quite a few places, where we use the number 1 here, and we're going to change that 1 to gap, and that gap is going to be passed in as a parameter. And to keep, just the original shell sort, gap is going to default to the value of 1. So with the insertion sort that takes a gap parameter, all we have to do for shell sort is that to call it repeatedly with a different gap. And the gap that we start with will be the length of the iterable divided by 2. We start at half the length, and then we call, and as long as the gap is bigger than 0, the smallest one we want is 1. So we just call the insertion sort with the gap, and then to prepare for the next iteration, we have the gap. So that's it for shell sort. It's pretty simple once we have the insertion sort. Now, as usual, we like to test our code once we have a testable unit of code. So can you pause the video? Go ahead and test shell sort. It's very simple given we have already written it, all the tests. So that's it, 2 lines of code. We create a shell sort test case and we set the sort function to shell sort. And I've already written it up. Well, this is the shell sort implementation and the shell sort test. We can actually run it. And because it's fast, we can actually see that everything tests out. Obviously, it didn't work the first time, but I've debugged it enough that it now works. Now, the interesting thing is to look at how it performs and compare it to insertion sort. So these are the performance number here, and when we put it on the same chart as insertion sort, you can see, if you look at the largest one, is shell sort is many times faster, and this is about 70 times faster. I think your readings claim even bigger speed up, and that's probably again because I have a very old laptop here, and you look at it, it takes so little time compared to insertion sort. Is like 2 orders of magnitude of difference. Okay, when you think about this, it's kind of may not make a whole lot of sense because we just put an insertion sort in a loop, and somehow that makes it faster and much faster than insertion sort, a single insertion sort, right? Something there just this doesn't seem to make sense. And especially consider, you can say there's something about a gap, but at the very last step, we know the gap is 1, and that is just a plain vanilla insertion sort. So how is that possible? How is that we do more insertion sort, but it's faster? But as we see from our experimental data, that's indeed the case. And concerning that very last step of insertion sort, even though the gap is 1, as we've seen from the animation and as we've talked about many times, that the insertion sort, if the elements are nearly sorted, it's actually O of n, not O of n squared. And in the case of shell sort, at the very last insertion sort, the elements are nearly sorted. So there are 2 kind of hopefully intuitive reasons why shell sort is so much faster. So the first one is something that we've said repeatedly already, that in the earlier passes, we moved the items a much greater distance right? Because of the bigger gap. Now, also these earlier passes, they sort a smaller list, right? They don't sort the entire list. This one actually says, the earlier passes actually do a lot of work, but they don't spend a lot of time doing it. Now, the second reason, it may or may not be obvious, but when you think about it, it should make sense. That is, as we're moving from larger gaps to smaller gaps, the ordering with the smaller gaps, they do not break the ordering in the one with the larger gap. So, for example, the elements that are already in the fourth sorted list, they are not moved relative to each other, right? They can still move, but they are not moved relative to each other when the insertion by the insertion sort with a gap of 2 or 1, anything less than 4. But those elements, they no longer have to move relative to each other. So these two together kind of is the one that gives the shell sort. However, the worst case of shell sort is actually n squared, as we will talk about next. So let's think for a moment, what is the worst case for shell sort? Well, if the earlier passes in the shell sort somehow do not move anything, in that case, well, then the last step with a gap of 1, that kind of degenerates the entire shell sort into a single normal insertion sort. So that will be the absolute worst nightmare for a shell sort. Now, how can that happen? Well, when you think about it, shell sorts, it does not compare or move elements right next to each other, right? Until the last insertion sort where the gap is 1, right? So we can create a worst case scenario for shell sort if, and this we need kind of a power of 2 number of elements in the list. So if we have that kind of list, and then if we kind of just put the for all the even positions has 1 number, and for all the odd number positions it has a different number, such as this list, 199, 199, 199, 199. Okay, so in this case, 1 and 99, they are not moved at all until the very last insertion sort. And if you don't believe me, try to run through the shell sort algorithm on this list and see when you actually end up moving anything. And let's actually test it. So I actually wrote 2 additional tests in the shell sort test case. So the first one is, so both of them, we start with a length that is power of 2, 128, and it goes up to the 16,000 or so, whatever the power of 2 in the 16,000 range. So in the first test, I generate random numbers, totally random numbers, and we time measure the time it takes to do that. And then in the second test case, I'm going to put just a small number at the odd, at the even. It starts at 0 at the even index, and then a larger number, 99, at the odd indexes. And yeah, I use list multiplication to create a big list. And then again, I also measure the time it takes to do that. And if you look at this, and especially look at just the last line here, the 16,384 items, with the random data, it's still pretty fast, right? But with the carefully constructed worst case nightmare for shell sort, it takes a lot longer.